Okay, so let's start. So last time we had finished with classification of the finite dimensional representations of the Lorenz group and SU2 times SU2 by constructing them as representations of the Lie algebras of SO31 and SO4. So today, we're going to extend the Lorenz group into what's called the Ponca group. So here, the main idea is very simple. You know, if you have a physical system, let's say a closed physical system, you know, its behavior is described by physical laws, some equations describing the properties of the objects in that system and how they interact and so on. If you translate that system to some other point in space or another point in time, without any additional external forces acting on it, the system should still be described by the same physical laws. So in other words, we expect most physics, essentially all physics except gravity, to be space-time translationally invariant. And so including translations in space and time extends the Lorenz group symmetries to what's called the Ponca group. So in other words, operationally, we just take a space-time point, which is labeled by some 4 vector, and we shift the values of the space and time coordinates by a constant. One constant for each of the 4 directions. So covariantly, we write that as x mu goes to x mu plus a mu, where a mu is some arbitrary constant 4 vector. And we demand that this is also a symmetry. So if we take our Lorenz transformations, which I'm writing now in the fundamental representation, so the representation that acts on 4 vectors, and now we add translations, we get a group called the Ponca group, and a 4 vector x mu will transform by a Lorenz rotation. I don't know why I'm calling this lambda, it should be m. Well, let's call it lambda. I think I use lambda on the next page. Sorry for the slight inconsistency in notation. So x mu undergoes a Lorenz rotation, so either a boost, an ordinary rotation, or a combination of the 2, plus this translation. So in addition to the 6 parameters of the Lorenz group, the Ponca group contains, in addition, these 4 additional translation parameters. So it's a group of 10 dimensions in total. Sorry, I was calling this M. Anyway, I'll change that afterwards. So if we consider, so here I want just to explore a little bit the group structure, and then you can explore that a little bit more as an exercise. So if you have 2 Ponca transformations, that means we have to specify two Lorenz transformations, M and M prime, and two translations, A and A prime. Then the group composition rule is this one. And so obviously the two Lorenz transformations just multiply together in the standard way. But the translations now behave, I mean, they have this property that the composition of the translations is the Lorenz transformation of the first translation plus the second translation. And the point there is that the translated, we make the first Lorenz transformation where x goes to m prime x plus a prime, and then in the second transformation, the Lorenz transformation must act on the translated space-time coordinate. So we get the rule here. And if you try to ask, if for example, m comma a is the inverse of m prime comma a, then clearly m must be the inverse of m prime, but a, which has to be the inverse of a prime, is not just minus a prime, it's given by minus m times a prime, or minus m prime inverse times a prime. Okay. So this is basically the structure of how the transformations work, and I want you to just play around with the transformations and verify that the Poincare group actually has advertised a group. Obviously, space-time translations are non-compact. The A's can take any value from minus infinity up to plus infinity. So each of the A's lives in a copy of the real line, and so we get 4 copies of the real line, but they have a natural space-time signature 3,1. And the Lorentz group, O3,1, gets extended non-trivially. It's by these translations. And the reason it's non-trivial is precisely because of this group composition law, that the Lorentz transformations in O3,1 act on the translations in this way. So mathematically, that's usually written this way. This symbol here is called the semi-direct product. And we say that the Poincare group is a non-trivial extension of the Lorentz group. And it's obviously 10-dimensional because you have 3 rotations, 3 boosts, and 4 translations. Okay, so now we're going to talk about representations of the Poincare group, and eventually this will sort of conclude with the kind of a standard sort of particle representation, interpreting the representations in terms of properties of particles. So if D is an arbitrary representation of the Poincare group, so in other words, a set of matrices whose matrix multiplication obeys the group composition law, then the D's, as usual, we can think of them as exponentials of some Lie algebra generators. And now I've introduced on the right-hand side here some notation that we haven't met before for the generators of the Lorenz group. So I'm calling them small m mu nu. And to make contact with boosts and rotations, if I set one of the indices equal to 0, then I get 3 generators. Those are the boost generators. And if I set both of the indices mu and nu equal to a spatial direction, then I get the mij's. And there's 3 of them because it's, m12, m13, and m23. These are just the rotation generators. And notice I've put a factor of I here as well. And I've included the factor of 2, which accounts for the spin half representations when we need them. And so the omega mu nu's are 6 parameters, which are just the angles and the boost parameters. And now we've included the momentum generators as well, the translation generators, which I'm calling P mu, because later on we will actually identify these with momentum. So in total, these 10 generators are actually generalized angular momentum and ordinary Hall momentum. Are there any questions about what I've written down, what I've said so far? Okay, so now we're going to look at the Lie algebra of this group. Was there a question? No. So the Lorenz algebra, so here I've written down the algebra satisfied by these generators. The Lorenz algebra is given in the first line, A. Then it's obvious that translations commute with each other. So the order of translating doesn't matter. But because of this non-trivial action here, boosts will obviously not commute with, translations will obviously not commute with boosts and rotations. So we end up with this relation here, where eta is the Minkowski metric. Now, as I said, we're going to interpret the P mu as, so its spatial components as ordinary momentum, and P0 will be interpreted as energy, at least in units in which C is equal to 1. So algebra A, as I said, is the Lorenz algebra, but I want you to verify that this is the same. What I've written here is actually isomorphic to the Lorenz algebra. And then using the group composition rules for the Poincare group, you should also be able to check that B and C are also true. Okay, so now we're going to start getting on to how we classify the representations of the Poincare group. Now, in SU2 representation theory, a key role in characterizing representations is to notice that if you take the sum of the squares of the generators, so, you know, J1 squared plus J2 squared plus J3 squared, in any representation, that is a matrix which commutes with all of the other matrices. Therefore, it must be proportional to the identity matrix. And in SU2, the proportionality constant is the spin times the spin plus 1. And that's why we can characterize any SU2 representation by the spin of that representation. Now, this concept is true much more generally for Lie algebras. And in general, Lie algebras have, Lie algebras bigger than SU2 tend to have even more Casimir operators, so more than one. As we'll see, the Poincare group has got two quadratic Casimir operators. And yeah, these operators play an equally important role. And in particle physics applications, that means that we will label particle states in terms of the eigenvalues of these operators. So it's a very natural concept. And in the Poincare group, there are two such operators, which I'll call P squared and W squared. So P squared is simply the Lorenz invariant product of P mu with itself. So it's P upper mu, P lower mu. So this is Lorenz invariant because P squared has no free Lorenz labels, so it's a Lorenz scalar. So that's an important point. I hadn't made that before. If you have some function of variables which individually transform under Lorenz transformation, so they have Lorenz labels, but you form a combination of them, which is using the summation convention, which has no free labels, then it will be Lorenz invariant. Just like the interval is invariant and gives us the definition of what a Lorenz transformation is. So we're actually interpreting P mu as the energy momentum 4 vector. And we're actually going to think of the representations now as being characterized by the properties of the particles which are transforming in that representation. So, you know, when we were looking at Lorenz, the representations of the Lorenz algebra, we were in the back of our minds thinking of the spin of the representation. We were characterizing the representations in terms of the spin of the representation, or in fact the spins of the two underlying SU2 algebras. So let's think of then a particle that has energy E and momentum P. Let's first consider massive particles. So for a massive particle, we can always go to the rest frame of that particle in which its momentum is zero. So it's just the frame in which we're traveling along with the particle. So if pi is zero, I mean, the particle is moving along, which means it has energy. So E itself cannot be zero. So it must be somehow proportional to the mass. Well, in fact, it is directly proportional to the mass with a proportionality constant, which is just given by the appropriate powers of the speed of light required to get the units correct. So in the rest frame, P mu is given by the first line here. And therefore, E squared over C squared, which is also, this thing here is E over C. So therefore, we get that E squared over C squared is M squared C squared. Or if I take the square root, E equals MC squared. However, P squared is a Lorentz invariant, so it makes sense for any frame, and in a general frame, the particle will have some momentum pi. So if I put that in as well, it must also be true that E squared minus P squared times C squared is equal to M squared C to the fourth. So all I've done here is gone from a frame in which pi is zero to a frame in which it's non-zero, and use the fact that P squared is Lorentz invariant. So this is the general form of Einstein's relativistic energy momentum relation. So this formula is true for all particles, whether they have mass or not, in fact. So in any representation, P squared will be just given by M squared times the identity. So I made a comment here. We'll often use units in which C is equal to 1. So an important exercise is to verify that P squared actually commutes with, say, M mu nu. Anyway, from this we learn that we should label representation vectors for, at least for massive particles, by the mass, because that's one of the Casimirs of the Ponca algebra. But there's another one, which is called W squared. This one takes a little bit more to define. And we begin by constructing a 4-vector W mu which is called the Pauli-Lubanski vector. And it's constructed by taking an antisymmetric combination of m mu of the m mu nu's and the momentum generators. And we make the antisymmetric combination by using the epsilon tensor in 4 dimensions. So epsilon mu nu rho sigma clearly has 4 Lorentz labels. If you interchange neighboring labels, then it changes sign. So that's what I mean, that it's totally antisymmetric. And one fixes a convention by choosing, for some cyclic permutation of 0, 1, 2, 3, a +1 or a -1. So here we could fix a convention by saying that epsilon 0, 1, 2, 3 is equal to 1. And then that tells you what all the other values of epsilon is, because the 4 labels on epsilon have to be different in order for it to be non-zero. So it's very similar. It's the 4-dimensional version of epsilon ijk. It's also, by the way, I didn't say this, but epsilon is Lorentz. Well, epsilon is SO3,1 invariant. Put that in brackets. It's SO3,1 invariant, but not O3,1 invariant. In fact, maybe I'll just explain that. It's useful. All right. So in fact, let's have a little exercise here. If I take this 4-index object and I make a Lorenz transformation by some m mu nu, what's the formula for the right-hand side? Can someone come up with a formula for that? So we're used to transforming, you know, x mu, p mu. We know how that transforms. So but we haven't had so much experience with transforming quantities, I mean tensors, which are with more than one index. Yeah.
Since it is a 4th rank tensor, we would have like 4 coefficients of m in front of the epsilon.
Mm-hmm.
Should I say this? Say it what?
I have m, and then you said 4.
Yeah, 4 m's.
4 m's, good. I'm liking this.
And then
this is a lower index. And then
there would be the tensor in other indices like alpha, beta, gamma, delta. Okay.
Excellent. So, and what would be the label? Give me now. Complete the formula for me. I want to put the indices here. So you said alpha, beta, gamma, delta there. What do I have here? Oh, sorry.
That would be upper indices.
And now? What's the indices of this M?
Mu alpha, mu upper, alpha down, yeah, and so on for the next indices.
Excellent. Excellent. This is a perfect answer. So the point is that each index transforms individually under the usual Lorenz transformation, but we get the product because this object is called a tensor because it transforms in this tensor product representation. And that's what this is, the tensor product representation for objects with 4 indices. Now, this quantity here, because I've totally anti-symmetrized, is actually equal to this whole thing. Is actually equal to the determinant of M times epsilon mu rho sigma. So this is something you can verify this last step. So if M is in SO3, 1, this determinant is equal to 1, and epsilon will be invariant. Otherwise, for all the other elements which are not in SO3, 1, it will change sign. Because remember, the determinant is either +1 or -1. So in fact, eta mu nu and epsilon mu nu rho sigma is a true statement. I think it's a true statement. Well, yeah. So I mean, these are the only Lorentz invariant tensors in 4 dimensions. Every other Lorentz invariant is built from these, at least in the fundamental representation. Okay, that was just a small aside. What we were actually looking at is the Pauli Lubanski vector. So in the Pauli Lubanski vector, these 3 Lorentz labels are summed over by epsilon. We're using the epsilon tensor. Since all 3 of them appear both upper and lower. So for example, let's consider this W0. Let's consider the time component of the Pauli Lubanski vector. So that means I put the first label of the epsilon tensor to 0, which means the remaining 3 labels have to be spatial. So they can be 1, 2, 3, or any permutation of 1, 2, and 3. So I can write it as I've written it here. And this, so epsilon 0 ijk is essentially epsilon ijk in the spatial directions. So W0, there should be a half. What it does is it takes MIJs, which are just the rotational elements of the Lorentz group in the fundamental representation, and dots them into the momenta. So this is just the dot product of angular momentum and momentum, because both of them are given by three component objects. Both take. So in other words, we can think of it as the dot product of spin and ordinary momentum. So this quantity is something which is called helicity. So in other words, particles have both spin and they have momentum, and you can take the dot product of these two quantities and you get a quantity called, it's a closely related quantity to spin, but it's called helicity. And I think here we're going to use the notation H for the values of helicity. All right, so let's consider now a particle moving in some direction, and let's choose it to be the third direction for convenience. Then let's consider the action of W0 on some state of mass m. And up here, I've left the dots here because we're going to figure out what all these other labels are for different representations. So W0 is given by J dot P acting on the state. Well, the eigenvalues of momentum is just momentum. So that will give me the component of momentum in the third direction times J3, because J3 is in the third direction. And so we get the J3 eigenvalue for that state. We'll call that H. So the eigenvalues of W0 are given by the magnitude of momentum times this quantity H, which is called helicity. And we know the values of the spin operator. And the definition of the Lorentz invariant W squared is just W mu lower. And this operator is a Casimir, so it commutes with the 10 generators, as you can verify for yourselves. And in fact, if you compute it, this gives you the sort of spin Casimir multiplied by the mass squared for massive representations. So in the end, these are the important relations at the bottom. That we have the W squared eigenvalue is m squared times the spin Casimir. P mu is just P mu, because we're talking about momentum eigenstates. And W naught, as we just computed, is the magnitude of momentum times the spin of the representation. I mean, times the spin of the state, I should say, not the representation, the spin of the state. So massive representations are labeled by the full momentum, the spin, and the helicity. But the helicities themselves are determined by the spin, and since we can go to the rest frame for a massive particle, we end up with labeling them by mass and spin. So these are the key relations here at the bottom. Does anyone have any questions about that so far? Okay. Before we discuss the massless case, then let's take a break here, which is, we're still on a prime number because it says 43 on my clock. So should we let's take 10 minutes again, come back at 53. Pause the video. go on. So now those relations for m equals 0 tell us that w squared and p squared are 0. For massless particles. And so the spin sort of drops out. However, the helicity is still there. The helicity is there through the W0 relation, where W0 will be given by the energy times the J3 eigenvalue. Or in fact, you see, for a massless particle, there's no rest frame, but we can always go to a frame in which, say, 2 of the 3 momenta are 0. So massless particles are always moving, and the component of momentum is either plus or minus the energy of the particle, and the energy is always positive. So for massless particles, we label the representations by helicity and their momentum. And that's because W mu is proportional to P mu, which makes helicity an invariant concept for massless representations. And because of the fact that it depends on the direction of the momentum, one gets a positive helicity state and a negative helicity state for a massless particle that has a non-zero spin. So, for example, a photon, which is a particle of spin 1, can either be left polarized, meaning its helicity is minus, which we could say define that to be helicity minus 1, or right polarized, helicity equals plus 1. And these are the two polarization, the two possible polarizations of a photon. So helicity and polarization are the same concept. Similarly, gravitons, even though we've never seen a graviton, but we believe that they exist. A graviton is predicted to be a spin 2 massless particle, and it will have 2 helicity states, which are plus and minus 2. This I've already said. To complete what I want to say about representations of the Lorenz group and Ponca group, I want to talk about representation in terms of differential operators. will add a up until now, we've been talking about matrix representations. One can also represent these symmetries in terms of differential operators. And differential operators, they act on functions and functions, vector fields, tensor fields, and so on. The fields that we will be introducing when we start talking about fields. So in quantum mechanics, we usually represent the Hamiltonian and momentum operators in terms of d by dt and d by dx with appropriate factors of square root of -1. So with that in mind, we can represent in a more covariant way the momentum operator as the square root of -1 times d by dx mu. Here, I've also set h bar equals 1. So the combination of h bar and c being 1 is a unit system called natural units, in which we can convert any dimensionful quantity into, for example, some power of energy or some power of length. Okay, so momentum can be represented by this operator. Similarly, the Lorenz generators can be represented by this combination of x mu and d by dx mu's. So as I said, being operator representations, they're acting on functions of x mu. And so the representation space is essentially infinite dimensional, because it's essentially the space of functions. I mean, when one is doing explicit problems, one doesn't just consider the space of functions. One should probably, one restricts to well-defined function spaces, depending on what the application one has in mind. For example, one might want to consider infinitely differentiable functions. So in other words, smooth functions. Or one might restrict to functions. You might only need to, depending on what analysis you're doing, consider functions which are differentiable twice. So by taking these operators, in particular m mu nu, one can verify that the Poincare algebra is satisfied by these differential operators, and that will be another exercise to do. Okay, so for the moment, that we're going to finish. This sort of finishes what we're going to say about representation theory of Poincaré and Lorenz. Before we get on to fields, which is going to be the topic for essentially the rest of the course, I want to do a small session on relativistic kinematics, so the physics of relativistic particles, in a sense. But does anyone have any questions about Lorenz and Poincaré before we move on?
Professor, I wanted to ask if the M0I matrices have any interpretation, just like the MIJ are angular momentum, the PI are linear momentum.
Oh, M0I are the boosts. I said that somewhere.
Right, but can you associate them to any physical quantity, like the other?
Oh, any physical quantity? Well, I mean, they don't, there's no invariant of a boost transformation, so they don't show up as they don't have any sensible interpretation in terms of their eigenvalues and so on. At least not for these, not for the representations we're talking about here. There are what are called continuous spin representations of the Poincaré group, but they don't seem to play any significant role in particle physics, but they do exist. We won't be talking about them at all.
No, thank you.
Any other questions before we move on to some relativistic kinematics? Okay.
Sure. Then, when we are about the Lorenz transformation, then if a Lagrangian is invariant under the Lorenz transformation, then there must be associated with some physical quantity that is conserved. That is. So I think there must be some conserved quantity or conserved current corresponding to the boosts.
We will talk about the conservation laws of Lagrangian when we get to Lagrangians. So.
Okay. So.
All right. So this section has a different flavor to the most of the stuff we've done so far. This is much more sort of physical, but these are just some concepts that are important implications of relativity for particle physics. So most particles in nature are actually unstable, meaning that particles can decay into other particles. And this process will go on until you're left with just stable particles. So in the standard model, the only, according to the standard model, the only stable particles are predicted to be the photon, the gluon, the electron, the positron, some combination of neutrinos, and the up quark. All of the other particles in the standard model are unstable. For the gluon, so for the photon, first of all, these are just predictions. It's essentially impossible to prove that a particle is exactly massless because our experiments have limited capabilities in precision. So it's essentially impossible to measure an observable which is predicted to be identically zero. You can measure it with some precision. So in the case of the photon, since photons are easy to see and detect, we have strong limits on the lifetime, on the mass and the lifetime, and which are very, very good. In the standard model, the reason that a photon cannot decay is firstly that it's massless, and secondly, given the quantum numbers of a photon, namely its helicity +1 or -1, and it's massless, there's nothing that a massless particle can ever decay into because it has zero mass, essentially. But the electron, which is a massive particle, and its antiparticle, the positron, it is predicted to be stable because it's the lightest charged particle in the standard model. So since charge is conserved and there are no lighter charged particles, the electron is stable. For neutrinos, so now we know that neutrinos have an upper bound on their mass, on their masses, but we haven't actually measured the individual masses. But we know that there's some neutrino which is very light and has a very low mass, much lighter than any of the other fermions in the standard model. So because there are no other known lighter fermions, the neutrino cannot decay. Gluons are the gauge bosons for the strong interactions, and since the gauge symmetry associated to the strong interactions is believed to be unbroken, gluons at the fundamental level are believed to be stable, and similarly quarks are the lightest fermions that participate in the strong interactions, and so they cannot decay either because there's no lighter such particles. Quarks and gluons are different to photons, electrons, and neutrinos in some sense because the strong interaction is so strong that we don't observe elementary quarks and gluons at low energies. What we instead observe are composite states like baryons and mesons. And you'll learn more about those things as the courses go on. Now, talking about the standard model, there are many particles in the standard model. I've only listed the ones which are believed to be stable. So the fermions of the standard model are grouped into quarks and leptons. And these come in, as we'll see, in 3 families. So most of you will have seen these. So there are 6 types of quark, 6 types of leptons, and you also have the antiparticles of all of these. I'm going to now write down the charges of all of these in units in which the electric charge of the electron is -1. And I'm going to give some indication of the masses of these particles. But I'm not being, if you want to find out the precise masses as currently known, you can look it up. And I'm going to use electron volt units. So roughly speaking, maybe less roughly speaking, so 939, maybe 8. Roughly speaking, 940 mega electron volts equals proton mass. So this is like 2 MeV. So you notice there's a big jump from here to here in masses. This one is few GeV. So the charm quark is like 1,000 times heavier than an up quark. This one the top quark is the heaviest known elementary particle. So its mass is like it's like 500,000 times heavier than an electron. And the neutrino masses are sort of all less than 0.1 eV, but greater than 0. So from this, you can see that you have all these heavier fermions towards the right of the diagram compared with the left of the diagram. There's also gauge bosons. So we have photon, neutral, and has 0 mass. Gluon, neutral, 0 mass. But then we have W plus and minus. There's a mass of about 80 GeV. And we have Z, 0, which has a mass 91 GeV. Finally, there's the Higgs, neutral, mass of about 125 GeV. Okay, so this is a very rough and quick introduction to the characters in the standard model. In the context of field theory, each one of these particles is described by a different field. So there's a field for each one of these. That's just some useful information for going forwards. So decays in the standard model. So a W plus boson can decay into a positron and an electron neutrino, and similarly with the other lepton families. It can also decay into an up quark, up type quark. C, and a bottom type quark, or actually a bottom type anti-quark. Now the mass of this thing is like 80 GeV, 80 giga electron volts in natural units, of course. And you see that the pairs of objects on the right-hand side, their masses are much less than 80 GeV. So, and that's because if you have a W boson at rest, the things it can decay to, their total mass has to be less than the W boson mass. And that's because of energy conservation. So if I have the W boson energy momentum 4 vector, that then has to, so let me write this in a better way. That then, if I consider, say, the first decay channel, say E plus nu, now this nu is not a Lorentz label. This means the electron neutrino. So in fact, because energy and momentum have to always be conserved, these two, the left-hand side, which is the energy and momentum of the state before the decay, has to be the same as the energy and momentum of the state after the decay. And the energy and momentum of the state after the decay is simply the sum of the energy momentum vectors of the two particles. So we can write this as P mu of the W equal to P mu of E plus P mu of mu electron. Does anyone have any questions about that? So this is the simplest type of decay, which is a two-body decay. And of course, this applies to any situation with a two-body decay. The initial particle P mu has to be equal to the sum of the P mu's of the decay products. And that's also independent of the number of decay products. So, by the way, this diagram here is essentially the Feynman diagram for this process. And this vertex, these interaction vertices for all of these processes are, you derive them once you are able to write down the Lagrangian for the standard model, which is something that you will do in the standard model courses. Notice that I did not write here the top quark, and that's because top quark has a mass which is bigger than the W boson mass. But I can write down a diagram involving the top quark and that involves W bosons, just to give you an idea. So top quark can decay into a W boson and a down type quark. For example, the bottom quark. I wrote the bottom here because this is the dominant decay of a top quark, it happens. And then from this process, the W will further go on to decay. Now, if the W had decayed into a muon, for example, then this muon is also going to decay because it's not stable. And muons actually undergo a three-body decay into, well, there are some possibilities for this, but one of them well, the most dominant one is the one that I'm writing here. Mu R mu. So you see, when a top quark decays, it's actually a complicated process that produces a lot of particles. I didn't talk about what happens to this B quark. This B quark essentially will convert into some number of mesons and baryons. in a very complicated process that is still not theoretically understood because we don't know how to analytically solve the strong interactions, or QCD. But in general, the P mu of the top quark here will be equal to the sum of the P mu's summed over all of the final states. Just to finish, so these are just two sample decay processes in the standard model. I'll just write down one more, which is the Higgs decay. And here I'll draw a blob. So Higgs, I'm choosing this one because this is the one that was actually first measured with the most significance. So Higgs can decay into 2 photons. So here, well, and for all of these decays, one thing I didn't mention is that charge, and so here we've only talked so far about energy and momentum conservation, but spin or spin/helicity has to be conserved, as does charge, and charge in the more general sense, including the strong and weak interactions. So you see that in the W decays, the lepton channels, the particles all have charge 1, and you have charge 1 objects and charge 0 objects, so the total charge is 1. The up quark has charge 2/3, the down quark has charge minus 1/3, so the anti-down quark has charge plus 1/3, so 2/3 plus 1/3 makes 1. So charge is also conserved. And you can check that for this more complicated decay. And for the Higgs, now the Higgs here is decaying into 2 photons. I put a blob here because this process starts not at tree level, but at one loop, what's called one loop in the standard model. And here, the helicity is important because the Higgs has spin 0, it's a scalar, whereas photons have spin 1. But what's happening is, as I said, as we learned earlier, is that the helicities is what we use to characterize the massless representation. So these photons will have opposite helicities, +1 and -1. So I will set some exercises in determining, just give you some exercises to look at these types of equations, because that's actually how you actually end up doing measurements with elementary particles. So in the case of the Higgs to 2 photons, we use this relation. Let's call these gamma 1 and gamma 2. We use these relations to actually measure the mass of the Higgs. Can anyone think of how we would use these relations to measure the mass?
Maybe in the rest frame of the Higgs, we can find the norm of the 4 vector.
Yeah, sort of. You don't have to go to the rest frame because the mass of the Higgs is Lorentz invariant quantity.
Yes.
So what you actually see, the Higgs, when it comes out of a proton-proton collision or whatever, however you've produced it, it has a tiny lifetime, which is like 10 to the minus 23 seconds or something. So this process happens very, very quickly. And all you ever observe are the end products, which are these 2 photons. But if you have a precise enough measuring apparatus and the calorimeter, what are called the calorimeters of the 2 main LHC experiments, ATLAS and CMS, were designed precisely for this purpose, to measure these photons. It means you can measure the energy and momentum of these 2 photons precisely. I mean, up to some, experimental precision, but relatively precisely. So this is what you measure, and then you simply look at this quantity. So you just you measure the right-hand side, it gives you a 4 vector that you've measured, and you take the square of this, the Lorentz invariant square of this 4 vector. And when you look at what this thing gives you, it has and this thing peaks at m squared Higgs. So you get some distribution which has some peak. So you just do this for each event, one at a time, and you'll get a distribution and fit that distribution and get a measurement with some level of accuracy. So I'll set a few exercises on this sort of kinematics stuff as well, but that'll be for next. The later part of this week's homeworks. Let me stop the recording.